Welcome viewers, in this video we will see the details about the superposition theorem available in the circuit theory. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive, link is given in the description box. Now we'll go to the topic. The superposition theorem, we'll see the details about superposition theorem. In a linear circuit containing more than one source, the current that flows at any point or the voltage that exists between any 2 points is the algebraic sum of current or voltage that would have been produced by each source taken separately with all other sources are removed. So the superposition theorem is the name itself, superposition. In any linear circuit, either the current or voltage exists, there are n number of sources available, mean we can consider only one source at a time, remove the remaining sources, then consider the second source, remove the other sources, such that we need to find the current and voltage. So the final value is the algebraic sum. For example, we have two sources available, mean initially we need to consider only one source, we need to find either voltage or current. Then we need to consider only second source, by removing the first source we need to find current or voltage. So the final value is nothing but algebraic sum of the first current one and current 2. So that is the statement given by the superposition theorem, algebraic sum of current or voltage, right? So that is separately we need to find separately. We need to consider only one source, other sources are removed, right? So the removal of ideal voltage source mean it is short circuiting. So we need to remove either current source or voltage source. So if you remove the ideal voltage source, mean it is a short circuiting. After removing voltage source, we need to make a short circuit. So ideal, similarly removal of ideal current source mean replacing it by open circuit. If you remove the current source, we need to keep in the open circuit. Removal of practical voltage source or current source mean replacing by its internal resistance. For ideal voltage source and ideal current, there is no internal resistance. So that ideal voltage source mean short circuited, ideal current source mean open circuited. For practical voltage or current source mean it is replaced by the internal resistance. Right? So this is the statement given. Based on the statement, we need to remove the source. While removing, what we need to do is given clearly in the statement. Right. Now we'll go for the example circuit, example problem, so that we are able to understand clearly. So consider this linear circuit contain two voltage source E1 and E2. Our aim is to find the current flowing through this load resistor RL. That is a current IL we need to find. So this IL is due to E1 as well as E2. And other two resistors available R1 and R2. So according to superposition theorem, what we need to do? We need to consider only E1. E2 should be removed. Removed means short circuit. With only E1, we need to find what is the current flowing through the RL. The second step, E1 is removed. That means short circuited. Only we need to consider E2. With that E2, we need to find what is the current flowing through RL. So the algebraic sum of both the current is nothing but total current flowing through the load resistance RL. That is the statement given by superposition theorem. Considering E1 alone, then considering E2 alone, we need to find current. The algebraic sum of both the current is the total current flowing through RL. So that is the given. Now we will see how it is possible, how it is correct, right? So in this circuit, let us consider E1 is greater than E2. Let E1 be the greater than E2, so that IL is the load current flowing through the load resistance. This IL is nothing but load current flowing through the resistance, right? So the net voltage, so due to that the net voltage is nothing but E1 minus E2, because we consider E1 is greater and E2 is lesser, right? So what is the total resistance in the circuit? The total resistance is nothing but R1, RL and R2, right? The load resistance, apart from that another two resistors are available. So R1 plus R2 plus RL, right? So the voltage is E1 minus E2. The resistance is R1 plus R2 plus RL based on the circuit. Now we'll go for the further calculation, right? So based on that, what is the load current IL? The load current IL is nothing but I equal to V by R. V is E1 minus E2. The voltage is E1. We consider E1 is greater, E2 is lesser. So E1 minus E2 divided by resistance. Resistance is R1 plus R2 plus RL. So the normal Ohm's law. I equal to V by R. V is E1 minus E2. R is R1 plus R2 plus RL. Now we split these two terms. Here E1 minus E2 available. The terms are splitted. So E1 divided by R1 plus R2 plus RL minus E2 divided by R1 plus R2 plus RL. Right. So what is this? This is nothing but the considering only the voltage source E1. So that we can take it as IL dash. IL dash is the current flowing through the load resistor RL due to only voltage source E1. Similarly, this term is nothing but current flowing through the load resistance due to only E2. So that is taken as IL dash. So it is flowing in opposite direction, so that it is minus IL dash. The sum of these two is nothing but the total current flowing through the load resistance RL, that is IL. So this is the statement given by the superposition theorem. So while writing the equation, it is clearly we are able to understand this term is due to only E1, current flowing through due to only the source E1. This term current flowing through the load resistance RL due to only voltage source E2. So the sum of these two is nothing but IL. So in the problem we can do, first we can consider only E1. We can find IL dash. E2 is removed. Then consider only E2. E1 is removed. Find the term, that is IL dash, IL double dash. So sum of these two is the total current. Right. So this is the description given. Based on that description is verified with the equation. I will go for the further details. So from the equation, IL dash is the current flowing through RL because of E1 alone, flowing from A to B while E2 is 0. Right. So IL dash is current flowing through the RL because of only E1. E2 is removed, that is flowing from A to B, taken as positive. IL double dash is the current flowing through the RL because of E2 alone. Then E1 is removed but flowing from B to A, negative direction. Right. So IL is the current flowing through RL when both the sources are acting simultaneously. So by adding IL dash and IL double dash, we will get the total load current flowing through the load resistance RL. Right. This is the statement given by the superposition theorem. Right. Now we'll see that superposition theorem can be applied for finding the current through or voltage across a particular element in a linear circuit containing more than two sources. But this theorem cannot be used for calculating the power. Right. So the limitation is there. We are able to find either current flowing through the element or voltage across the element, having the two or more voltage or current sources in a linear circuit, but we cannot find the power in the circuit by using that. Superposition applicable only for current source or voltage source to find current flowing through the element or voltage across the element, not applicable to find the power. So in this video we discuss what is the statement of the superposition theorem, and also we verified with the example problem. Right. So that the total current is nothing but sum of the current due to source 1 and source 2. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the solved problem in superposition theorem using the DC source. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. The statement of the problem is find the current in 2 ohm resistor between A and B for the network using the superposition theorem. We need to find the current flowing through 2 ohm resistor. It is marked as AB. Now refer the diagram. So the network is available. We need to find this current flowing through this 2 ohm resistor. This termed as IL, right? This marked as AB. So the other 1, 2, 3, 4 resistors are available apart from the load resistor. 5 ohm, this 3 ohm, 4 ohm and 2 ohm. We have two voltage sources are available. 10 voltage source and 20 voltage source. So according to superposition theorem, what is the statement? So we need to consider only 10 voltage source alone. By removing 20 voltage source, we need to find what is the current flowing through 2 ohm resistor. In the second step, we need to remove this 10 voltage source, only need to consider 20 voltage source. For that, we need to find what is the current flowing through this 2 ohm resistor. So the total current is nothing but the current due to 10 voltage source and current due to 20 voltage source. We need to add both the currents. That is the statement of the superposition theorem. Now we will go to the step 1. So the step 1 is nothing but considering 10 voltage source, remove 20 voltage source and 10 voltage source only is acting, right? We need to consider only 10 voltage source. 20 voltage source is removed. What is meant by removal of 20 voltage source is short circuited. We need to short circuit the voltage source 20 voltage. Then we need to find current. Now we'll go to the diagram. After removal of this 20 voltage, the circuit is reduced, so that we'll see that what is the reduced circuit. So this here the 20 voltage source is removed and make it as short circuit. Now we have only the 10 voltage source is available. Now our aim is to find what is the current flowing through this 2 ohm resistor due to only 10 voltage source, right? So this circuit is further simplified that these 2 ohm and 4 ohm, these two are connected in parallel. This 4 ohm and 2 ohm are in parallel, right? So we can find this equivalent resistor. So that R equivalent is 4 into 2 divided by 4 plus 2. That is R1 into R2 divided by R1 plus R2. That is the equation for finding the equivalent resistance when two resistors are connected in parallel. So 8 divided by 6, it is 1.33 ohm, right? These 2 ohm and 4 ohm are connected in parallel. So that equivalent resistor is 1.33 ohm. So that is available here. So these resistors are connected. These two are in parallel. After simplification, the equivalent resistance is 1.33 ohm. Now the circuit is further simplified. Right. So our aim is to find this current through 2 ohm resistor. So we can use the loop method. Kirchhoff's voltage law, KVL using loop method. Right. So this is the first loop. The current is I1. This is the second loop, I2. Loop means closed circuit. This is the first loop, loop 1. The current flowing through the loop 1 is I1. This is loop 2, second loop. The current flowing through the loop is I2. So what is the current flowing through this 2 ohm resistor? I1 is flowing from top to bottom. I2 is flowing from bottom to top. So the difference, both are in opposite direction. So I1 minus I2 is the current flowing through 2 ohm resistor. So we need to find I1 value and I2 value. The difference between I1 and I2 is current flowing through 2 ohm resistor. See this, I1 is flowing downwards, I2 is flowing upwards. So the difference between these two is flowing through 2 ohm resistor. Now we'll go to the matrix method. We will go to the matrix method. So this is nothing but R into I equal to V. V equal to I into R. This is voltage matrix, current matrix, resistance matrix. Right. First we will see the resistance matrix. Right. What is that available here? What is this value? This R11. R11 means the total resistor available in the loop 1. That is 5 plus 2, 7. Right. This is R12. R12 means the resistor available between loop 1 and loop 2, commonly available. So this 2 ohm is commonly available between loop 1 and loop 2. So it's minus 2. So other than diagonal, other elements are negative. So it is minus 2. This is R21, same thing. The common resistor between second loop and first loop, that also 2 ohm resistor. So minus 2. Then R22. What is R22? The total resistor available in the second loop, that is 3 plus 1.33 plus 2, right? 3 plus 1.33, 4.33 plus 2, 6.33. Right? So this is the resistance matrix is formed. This R is nothing but total resistor available in the loop 1. 6.33 is total resistor available in the loop 2. These two is commonly available between loop 1 and loop 2. Then currents are I1 and I2. Here I1, I2. What is the voltage available in loop 1? 10 voltage. In loop 2 there is no voltage source. It is 0. Right? So this Kirchhoff voltage law, KVL method, loop method available, separate videos are available. Right? So here they are directly given. So we can take, this is the delta, del value, that is 7 minus 2 minus 2, 6.33. We need to find the del value. We need to simplify this. We have to find the determinant of this matrix. So 7 into 6.33 minus 2 into minus 2. There are already one minus is available here. This is also minus 2. This is also minus 2. Right? So 7 into 6.33 is 44.31 minus. So 3 minus available. So finally it is minus only. 2 into 2, 4. So after subtraction what we got? 40.31. The delta value is 40.31. Now we need to find the delta 1, delta 2 followed by I1 and I2. What is delta 1? Delta 1 is nothing but you have to replace the first column with the voltage matrix. That is delta 1. Replacing the second column with the voltage matrix is the delta 2. Right? The delta is as it is, we have to write. Delta 1 means first column is replaced by voltage matrix 10, 0. Second column is replaced mean delta 2. Right. So the delta 1 after replacing what we have, it is 10 minus 2, 0, 6.33. So one is minus 0 is there, only we need to multiply these two. 10 into 6.33 minus 2 into 0. So this term becomes 0. So 10 into 6.33 is 63.3. Del 1 value is 63.3. Then we have to find the delta 2. Delta 2 is 7, 10 minus 2, 0. So 7 into 0 is 0 minus of 10 into minus 2. Already here minus 1 is there, here also minus there. So 2 into 10, 20. Right? Now we calculated the delta 2 value also. Del value available, delta 1 available, delta 2 also available. Now we'll go to the current. From that we can find the current value. So I1 is nothing but delta 1 divided by delta. 63.33 divided by 40.31. Just now what we calculated. These two values are calculated. So that it is 1.57 ampere. By dividing this we got 1.57 ampere. Similarly I2 is delta 2 divided by 2. So 20 divided by 40.3, that is 0.496 ampere. Now we calculated I1 and I2. We already discussed current flowing through the 2 ohm resistor due to 10 voltage source alone is nothing but, that is we taken as I dash, right? The 20 voltage source is I double dash. So that is the difference between these two current, because both the currents are flowing in opposite direction. I1 minus I2. I1 value is 1.57. I2 value is 0.496. So the difference is 1.076 ampere. So this is the current flowing through the 2 ohm resistor due to only 10 voltage source. Only the 10 voltage source. Right. Though the step 1 is completed. We consider only 10 voltage source. We calculated what is the current flowing through the 2 ohm resistor due to only 10 voltage source. Now we'll go to the second step. Considering 20 voltage source, removing 10 voltage source. What is the removal of 10 voltage source? Is nothing but short circuit. Right. Now we need to consider only 20 voltage source. 10 voltage source is removed and short circuited. Now we'll see the diagram. After this, what is the equivalent diagram? We'll see that. So after removal of this 10 voltage source, this is short circuited. Only 20 voltage source is available. Right. The further simplification, same thing what we did in the step 1. This 4 ohm and 2 ohm are in parallel. So that is simplified. That the equivalent value is 1.33 ohm. right? So these two the resistor now become 1.33 ohm, right? Same thing we can apply the Kirchhoff's voltage law. This is the loop 1, the current is I1. This is loop 2, loop means closed circuit, the current is I2. The current direction what we is taken as same direction, we are not taken in the opposite direction. We can take in the opposite direction also, because source is available here. Normally the current will flow in this direction, but we taken the current in the same direction. That is our wish. If you take the current direction wrongly, you will get the negative current, negative value. So that is not a problem. We can take either any direction. So the current is taken as clockwise direction only, right? So see, this I1 current is flowing from top to bottom. I2 current is flowing from bottom to top. Same thing. So the difference between these two current is flowing through 2 ohm resistor. What we discuss in the step 1, same thing only. So now we need to form the matrix, right? So this resistance matrix, current matrix and voltage matrix, right? So that the resistance matrix is that. What is that R7? This is R11. The resistance available in the loop 1, 5 plus 2, 7. What is this 6.33? Resistor available in the second loop, 3 plus 1.33 plus 2. So 2 plus 3, 5, 5 plus 1.33, 6.33. This is nothing but R12 and R21. They are the resistor commonly available between loop 1 and loop 2. This 2 ohm is commonly available. So minus 2, minus 2. The current is I1, I2. The loop 1, there is no voltage source, 0. Here, the loop 2, 20 voltage is available, minus 20. Why it is minus 20? See the current direction. Current is going from top to bottom. That is plus to minus, right? Positive potential to negative potential. So that it is minus 20. If it is from negative to positive potential, previous case, it is negative to positive potential. So that plus 10 voltage. Here going from plus to minus, right? See the direction, it is downwards. So current is flowing from positive potential to negative potential. It is a drop in potential. So that minus 20, right? So this is nothing but our del value, right? So the del value, first we will find the del value. 7 minus 2 minus 2, 6.33. So this is very similar to the previous case. 7 into 6.33 minus of minus 2 into minus 2. So this value is 44.31 minus 4, it is 40.31. Very similar value in the previous step 1 also. Del value is 40.31. Now we need to find the del 1 and del 2. What is del 1? Replacing the first column with the voltage matrix is del 1. Replacing the second column with voltage matrix means del 2. Right? So the del 1 and del 2 replacing the here first column is replaced by voltage matrix. Second column is replaced by voltage matrix, that is del 2. Right? So 0 minus 2 minus 20, 6.33. So 0 into 6.33 minus of minus 2 into minus 20. Right? So this term is 0. So 3 negatives available. So finally negative only 40, minus 40. Del 1 value is minus 40. Del 2, 7, 0, minus 2, minus 20. 7 into minus 20, minus of 0 into minus 2. Right? This value is 0. So 7 into minus 20, minus 140. Del 2 value is minus 140. See this? In both the case we got the negative value. That means the current what we taken as wrong. It is opposite direction. But it's not a problem. By seeing this negative value, we can able to understand the current is flowing in opposite direction what we marked in the circuit. So from this value we can find the now I1 and I2 value. Current I1 and I2. So I1 is nothing but del 1 divided by del. I1 is the del 1 divided by del. Minus 40 divided by 40.31. Minus 0.992 ampere. Right. Similarly I2. Del 2 divided by del. Minus 140 divided by 40.31. So minus 3.47 ampere. Right. Now we calculated I1 and I2. What is the current flowing through 2 ohm resistor? We already discussed. There are two currents are flowing. I1 is flowing downwards. I2 is flowing upwards. So the current is the difference between I1 and I2. So due to 20 voltage source, we are taken as I double dash. I dash means current flowing through 2 ohm resistor due to 10 voltage source. I double dash means due to 20 voltage source, right? So we need to find the difference. Already minus is there. Minus 0.992 minus of minus 3.47. So the final value is 2.47. So the current flowing through 2 ohm resistor due to only 20 voltage source is 2.47 ampere. Now we calculated two currents, I dash and I double dash, due to 10 voltage source and 20 voltage source. So by the superposition theorem, the total current flowing through 2 ohm resistor is IL dash plus IL double dash. What we calculated, we need to add both the values. So IL dash is 1.076, IL double dash is 2.478. So by adding this, we got 3.55 ampere. Right, so the total current flowing through the 2 ohm resistor due to 10 voltage source as well as 20 voltage source is 3.55 ampere. So by superposition theorem, we are easily calculating, by considering only one voltage source, we are calculating the current. Then considering the another voltage source, calculating the current by the simplified manner. Thereafter, we are adding both the currents. That is a statement given by superposition theorem. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the solved problem based on the superposition theorem using the DC source. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. The problem is, compute the current through 23 ohm resistor for the network shown below by the superposition theorem. The network is available here. 1, 2, 3, 4 resistors are available. We need to find the current flowing through this 23 ohm resistor. So this is taken as a load resistor. There are two sources available. One is current voltage source, 200 voltage source available. Another one, 20 ampere current source is available. So based on the superposition theorem, first we need to consider only this 200 voltage source by removing 20 ampere current source. We need to find what is the current flowing through 23 ohm. Then the second step, we need to consider only 20 ampere current source. We have to remove the 200 voltage source. Then again we need to find what is the current through 23 ohm resistor. So the final value is sum of these two currents. So that is the procedure. So we will go to the step 1. The step 1 is nothing but considering the only 200 voltage source, removing 20 ampere current source. So in the step 1, we are going to remove this 20 ampere source. We are going to consider only 200 voltage source. What is meant by removal of this current source is nothing but open circuit. While removing the current source, we have to make it as open circuit. Voltage source means short circuit, right? So after removal of this 20 ampere current source, we will see the diagram, equivalent diagram. So this 20 ampere voltage, 20 ampere current source is removed and kept as open, right? Now we need to find our aim is to find the current flowing through 23 ohm resistor. We will follow the Kirchhoff's voltage law, loop method. Loop means closed circuit, KVL, Kirchhoff's voltage law, loop method we can follow. So this is the first loop. The closed circuit is the first loop. This is the second loop. Contain 47 ohm, 4 ohm, 23 ohm and 200 ampere, 200 voltage. This is the second loop. This is the open circuit, so current will not flow through the open circuit. Now we need to frame the matrix. V equal to I into R. Voltage matrix, current matrix and resistance matrix. This resistance matrix is nothing but this is R11. R11 means the resistor available in the loop 1, first loop. What are the resistors available in loop 1? 47 and 27 and 47. So the sum of these two, 27 plus 47 is 74. This 74 is the resistor available in the second loop. Sum of resistors available in second loop. 47 plus 4 plus 23. 47 plus 4, 51 plus 23 is 74. This 47 is the commonly available between loop 1 and loop 2. This 47 ohm is available in loop 1 as well as loop 2, commonly available. So minus 47. Other than diagonal, all elements are written as negative. So 74 minus 47 minus 47, 74. The current is the loop 1 I2, loop 2 is I1, I2. Then voltage source. What is the voltage source available in loop 1 is 200 amp, 200 voltage. And see the current direction. Current is flowing from top to bottom, that is plus to minus, positive potential to negative potential. So it is a drop in voltage. So minus 200. In loop 2, current is flowing in this direction from bottom to top, negative to positive. So it is rise in potential, 200 plus 200, right? So loop 1, current is flowing downwards from plus to minus, so minus 200. In loop 2, current flowing upwards, that is negative to positive, so plus 200. Now we frame the matrix. Now we can, this is nothing but our delta value. This Kirchhoff's voltage law, loop method separately available. Separate videos are available. So this 74 minus 47 minus 47, 74 is the del value. We need to find the determinant. 74 into 74 minus of minus 47 into minus 47. Right? So this value is 5476. This value is 2209. Negative. There are 3 negatives available, 3. So that finally negative only. So the del value is 3267. This is the del value. Next one we need to find del 1 and del 2. What is del 1? First column is replaced by voltage matrix. So this first column is replaced by voltage matrix, that is called del 1. Similarly, if you replace the second column, that is del 2. Right? So we'll see that del 1 and del 2. See, the second column is replaced by voltage matrix, that is del 2. Now we'll find the del 1 value. 200 into 74 minus 200 into 74 minus of minus 47 into 200. So after simplification, what we got? 5400 minus 5400. Similarly, del 2, second column is replaced by voltage matrix. 74 into 200 minus of minus 200 into minus 47. So that value also same, but it is positive. 5400. Del 2 value is 5400. Here minus 5400, here plus 5400. From del 1 and del 2 value, we can easily calculate the I1 value, current in the loop 1. I1 is del 1 by del, minus 5400 divided by 3267, that is minus 1.65 ampere. Similarly, I2, del 2 by delta, 5400 divided by 3267, plus here minus is there, plus 1.65 ampere. So now we calculated the loop current I1 and I2. Now we need to see what is the current flowing through 23 ohm resistor. That is our requirement. So the current flowing through 23 ohm resistor due to 200 voltage source is IL dash. We termed as IL dash. IL double dash means due to current source. IL dash means due to voltage source. It's nothing but I2 because 23 ohm is available in the loop 2. So the current in the second loop I2 is nothing but IL dash, current flowing through 23 ohm resistor. We already discussed in the circuit diagram. The current flowing through 23 ohm resistor is nothing but I2. So 1.65 ampere is flowing through the 23 ohm resistor due to voltage source alone. That is called IL dash. Now we'll go to the second step. Considering only the current source, removing the voltage source. Removal of voltage source means it is a short circuit. We need to make a short circuit. We will see the circuit diagram. After short circuit, what will happen? So here the voltage source is there, that is short circuited now. Right? This current source alone we consider. Now again we need to find what is the current flowing through this 23 is not 24, 23 ohm resistor. Right. Now we need to simplify this circuit. In order to find the current flowing through, we need to simplify. In step 1, we followed the Kirchhoff's voltage law, loop method. But here current source is available. No need to go for loop method. By simplifying the circuit, we can find the current flowing through the 23 ohm resistor. Right. Now we'll see how to simplify this. So in the simplification process, by seeing the diagram, this 27 ohm and 47 ohm are connected in parallel. So we can go for a simplification of equivalent. We can find the equivalent resistance because of parallel combination. 27 ohm and 47 ohm are connected in parallel. So the equivalent circuit, equivalent resistor is 27 into 47 divided by 27 plus 47. That is R1 into R2 divided by R1 plus R2. So after simplification, what we got? 17.4 ohm. Right? Now these two parallel resistors are replaced as 17.14 ohm. Now seeing this diagram, these two are connected in series. Is 17.14 and 4 ohm. So that it is 21.14 ohm. This 17.14 and 4 ohm is connected in series. So that it become 21.14 ohm. Now see the circuit diagram is simplified. Here 20 ampere is available. So at this place what will happen? The current will be divided. The current will be divided. Some of the current will flow through 21.14 ampere. Some of the current will flow 23 ohm resistor. Right? Now we'll see that what is the, we can use the current divider rule. We can use the current divider rule here. Right? So using the current divider rule, current flowing through the 23 ohm resistor. So our aim is to find the current flowing through 23 ohm resistor. So what is that? IL double dash. IL dash we already calculated due to voltage source. IL double dash is the due to current source. Total current multiplied by resistance of the opposite branch. So our aim is to find the current flowing through 23 ohm resistor. So we have to multiply with other branch resistor 21.14 divided by total resistance 21.14 plus 23. Right? In voltage divider rule, the same voltage we have to, same branch resistor we have to multiply. Here opposite branch resistor should be multiplied. Right? So the total current multiplied by resistance of other branch divided by total resistance. Right? So after simplification, what we got? 9.57 ampere. So the current flowing through 23 ohm resistor due to only the current source 20 ampere is 9.57 ampere. That is IL double dash. Now we calculated IL dash as well as IL double dash. Now we can calculate the total current. Therefore the current through the 23 ohm resistor is I equal to IL dash plus IL double dash. That is 1.65 what we calculated in the step 1. 9.57 what we calculated in the second step. Both are added together. So 11.22 ampere. So this is the current flowing through the 23 ohm resistor due to voltage source as well as current source. So in this problem we discussed the superposition theorem using DC source. There are one current source and one voltage source is available. Initially we consider only voltage source. We remove the current source, that is kept as open. We calculated the current using KVL, Kirchhoff's voltage law. In second method we consider only current source. Voltage source is removed, that means short circuited. So by simplifying the circuit itself, we can able to find the current flowing through 23 ohm resistor. The circuit is simplified. Finally we implemented with the current divider rule. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the solved problem in superposition theorem using AC voltage source. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Calculate the current through 2 ohm resistor of the network shown below using the superposition theorem. So the network is given here. There are two voltage sources available and resistor and inductors are available here. Here resistor and capacitor is connected. This 2 ohm is the load resistor. Our aim is to find the current flowing through this 2 ohm resistor using the superposition theorem. So we know that superposition theorem, if the two voltage sources are available, mean we need to consider one source at a time, we need to find the current. So based on that, current flowing through the 2 ohm resistor I equal to I dash and I double dash. I dash is nothing but current due to 5 voltage source only. We need to consider only 5 voltage source, that is 10 voltage source is removed. I double dash is current due to 10 voltage source only considering 10 voltage source, that means 5 voltage source is removed. So in the step 1 we need to consider only 5 voltage source, 10 voltage source is removed, that is short circuited. In the step 2 we need to consider only 10 voltage source and removing the 5 voltage source, that means the short circuit. Now we'll go to the step 1, that is considering only the 5 voltage source. So step 1, considering only 5 voltage source and removing 10 voltage source, that is short circuited. So here the 10 voltage source is short circuited, only we have 5 voltage source is available. Our aim is to find the current flowing through 2 ohm resistor. So we can use the Kirchhoff's voltage law, loop method, closed loop method. So this is the loop 1. Loop means closed circuit. This is loop 2. The current in loop 1 is I1, current in loop 2 is I2. So we can frame the equation for loop 1 and loop 2 using the Kirchhoff's voltage law, KVL. So first we will apply the Kirchhoff's voltage law to the loop 1. That is nothing but applied voltage equal to voltage drop. That is the Kirchhoff's voltage law, right? So here the I1, current I1 is flowing through the loop 1. So we need to find what is the current flowing through this 2 ohm, the inductor 2 and resistor 3 ohm and this resistor 5 ohm and this capacitor minus 2J, right? So in this, here the current I1 is flowing through this inductor and resistor. So that 2J into I1 plus 3 into I1. In this 5 ohm resistor, this I1 is flowing as well as I2 also flowing. This arm is available between loop 1 and loop 2. I1 is flowing from top to bottom. I2 is flowing from bottom to top. Both are in opposite direction. So the difference in current I1 minus I2 is flowing through this 5 ohm resistor and this capacitor. So that it is 5 into I1 minus I2. Similarly, minus 2J into I1 minus I2. That is equal to voltage source 5 ohm, 5 voltage. Right? So in inductor and resistor only I1 is flowing, but this resistor and capacitor I1 also flowing and I2 also flowing in opposite direction. So we are taking I1 minus I2. So after simplification we got 8I1 minus I2 of 5 minus 2J equal to 5 voltage. So equation number 1. We have I1, I2 into equal to voltage. Now we will apply the Kirchhoff's voltage law to the second loop. The second loop again this 5 ohm and this capacitor having two currents are flowing. In this 2 ohm only I2 is flowing. So 2 into I2 plus 5 into I2 minus I1. Here we are taking I2 as a reference. So that I2 minus I1. In previous loop I1 is reference. So I1 minus I2. Minus 2J I2 minus I1 equal to 0. There is no voltage source in the second loop. So that is equal to 0. So after simplification what we got? Minus 5 plus 2J I1 plus 7 minus 2J I2 equal to 0. Right? So we have equation 1 and equation 2. Now we need to solve this equation 1 and 2 for the further simplification. So this equation 1 is written 8I1 minus 5 minus 2J I2 equal to 5 minus 5 plus 2J I1 plus 7 minus 2J I2 equal to 0. Now we can write in a equation in a matrix format. B equal to I into R. Voltage matrix, current matrix, resistor matrix. So this 8 is written here. Minus is written, minus is multiplied out inside. So minus 5 plus 2J equal to into I1 and I2. Here 5 voltage is there, here voltage is 0. The second equation, minus 5 plus 2j, 7 minus 2j. So this is now the resistor matrix, this is current matrix, and this is the voltage matrix. Now we can find the delta value. This delta value is calculated here. So this is nothing but delta. We need to find the determinant. You have to multiply these two. 8 into 7 minus 2j minus of minus 5 plus 2j into minus 5 plus 2j. You have to multiply this. So after multiplication we got this value. We can go for further simplification. So for further simplification, delta equal to 56 minus 16j minus of minus 25 minus 20j plus 4 into minus 1 is multiplied. So after fully simplified, it is got 35 plus 4j. This is the rectangular form. It should be converted into polar form. That is, this is real term and imaginary term. This one angle, this magnitude and angle, 35.22 with an angle of 6.51. How to convert this rectangular to polar? It is available in a calculator. In the calculator directly you can calculate, you can convert from rectangular form to polar form. Manually how to convert this magnitude is nothing but square of these two values, real and imaginary term. Square root of 35 square plus 4 square. So that is nothing but this 35.22 value. Similarly the angle, how to convert tan inverse b by a, that is imaginary term by the real term. 4 tan inverse 4 divided by 35. So that is nothing but 6.15 degree. So rectangular to polar directly you can convert from calculator or manually, mean this is the formula, square root of the values and angle tan inverse b by a, 4 by 35. Now we'll come to the delta 2. Delta 1 is not needed. What we need is I2. I1 current is not needed. So directly we can go to delta 2. Delta 2 means the second column is replaced by the voltage matrix. This is the first column written as it is. Second column is replaced by voltage matrix. So 8 into 0 minus 5 into minus of minus 5 plus 2j. Right? So after simplification we got 25 minus 10j. In a rectangular form. In polar form it is 26.925 with an angle of minus 21.8 degree. So here also we can convert by using this formula. The same thing what we discussed. Square of the magnitudes. Tan inverse b by a. Now we calculated delta 2 also. Now we can calculate I2 value. From these two we can calculate the I2 value. I2 equal to delta 2 divided by delta. For the division we need a polar form. Rectangular form is used normally for addition and subtraction. For this division and multiplication normally we need the rectangular form, polar form, so that it is easier. So delta 2 is 26.925, angle of minus 21.8. Delta value is 35.22, angle of 6.51. So these two magnitudes are divided. 0.764. Angle you have to subtract. This angle is subtracted from this angle. Minus 21.8 minus 6.51. Multiplication means these two angles are added. Division means subtracted. That is the procedure. Right. So after subtraction what we got? Minus 28.31. 0.764 with an angle of minus 28.31. So this is the current. Therefore, current through 2 ohm resistor due to 5 voltage source only is nothing but I1 dash, that is equal to I2 equal 0.764 with an angle of 28.31. So this can be converted into polar form. This is polar form, rectangular form. 0.672 minus j 0.362. Here also directly you can convert from the calculator. Now we'll go to the second step. By considering the 10 ohm 10 voltage source. Considering only 10 voltage source by removing the 5 voltage source, that is short circuited. See this, the 5 voltage source is short circuited, only we can consider the 10 voltage source. Again here we can use the Kirchhoff's voltage law. This is the loop 1. This is loop 2. In loop 1, the current is I1. In loop 2, current is I2. First, we will apply the Kirchhoff's voltage law to the loop 1. So, here we have inductor and resistor. Only I1 is flowing through this inductor and resistor. So, 3I1 plus 2jI1. In this resistor and capacitor, as we discussed earlier, the I1 also flowing, I2 also flowing in opposite direction. So that 5 into I1 minus I2, this in this resistor. Capacitor minus 2j I1 minus I2 equal to this voltage source, 10 voltage, right? See this, the polarity top to bottom, negative to positive, right? The current is flowing from top to bottom, positive, negative to positive, rise in potential. So that 10J. So after simplification, we got 8I1 plus 5 plus 2j I2 equal to minus 10J, right? This is minus 10J. This is equation number 1. Similarly, we can apply the Kirchhoff's voltage law to the second loop. In the second loop, in 2 ohm only I2 is flowing, 2 into I2. But again, this resistor and capacitor, both I1 and I2 is flowing. So, I5 into I2 minus I1. Here, we are taking I2 as a reference. In loop 1, I1 as a reference. So, I1 minus I2. Here, I2 minus I1. Similarly, the capacitor minus 2j, I2 minus I1 equal to 10j. Right? After simplification, what we got? Minus 5 plus 2j I1 plus 7 minus 2j I2 equal to 10j. This is equation number 1. Right? So, now we can consolidate this equation 1 and 2. 8I1 plus 5 plus 2j I2 equal to minus 10j. Minus 5 plus 2j I1 plus 7 minus 2j I2 equal to 10j. So, it is written in a matrix form. This 8, this 5 plus 2j, minus 5 plus 2j, 7 minus 2j, I1, I2 equal to minus 10j and plus 10j. So, this can be formed. This is V equal to I into R, voltage matrix, current matrix and resistance matrix. Now, we will go for the further simplification. So, in the loop 1, current is flowing downwards, I1 is flowing downwards from positive to negative, so that minus 10j. In second loop, I2 is flowing from bottom to top, minus to positive, rise in potential, so plus 10j. Right? Loop 1, current flowing downwards, positive to negative, fall in potential. In loop 2, current is flowing from bottom to top. See, the current is flowing bottom to top, minus to plus, rise in potential, so that 10j. Now we can go for further simplification of this matrix. So this is the del, the resistor matrix is the del. So 8 into 7 minus 2j minus of minus 5 plus 2j into minus 5 plus 2j. You have to multiply this. After simplification, we got 35 plus 4j. So it is in a rectangular form. That can be converted into polar form. 35.227 with an angle of 6.519. So we already discussed how to convert from rectangular to polar. Directly you can convert from calculator, or procedure is there. Square root of 35 square plus 4 square. This angle is tan inverse 4 by 35. This delta value is very similar to step 1 also. Now we will go to delta 2. Delta 1 is not needed. I1 value is not needed. What we need is I2. So directly we can go to delta 2 value. So 8 minus 5 plus 2j. This second column is replaced by the voltage matrix, that is delta 2. First column we replace delta 1. So 8 into 10j minus of minus 10j minus 5 plus 2j. So after multiplication, after simplification, we got 30j minus 20 in a rectangular form. While converting polar form, it is 36.055 with an angle of 123.69. So this is the delta 2 value. From that we can calculate I2 value. Delta 2 divided by delta 36.055 angle 123.69 divided by 35.227 angle 6.519. I already told, for division or multiplication, polar form is necessary. For addition and subtraction, this rectangular form is necessary, easier. Rectangular form is easier. Polar form is easier for division and multiplication. So these two magnitudes are divided. 36.055 divided by 35.229. So it is 1.023. The angles are subtracted. 123.69 minus 6.519. That is 117.171. So this is nothing but I2. Current due to only the 10 voltage source minus 0.469 plus j 0.91, right? So that is in a rectangular form. Again it is converted into rectangular form. I2 equal to I2 dash. So the total current flowing through the 2 ohm resistor is I dash plus I double dash. This I dash is already calculated. I dash is already calculated in the step 1, 0.672 minus j 0.362. I double dash is calculated here, 0.469 plus j 0.91. So by adding these two, 0.205 plus j 0.547 in a rectangular form. Polar form it is 0.564 magnitude of the current. Angle is 69.45 ampere. Right? So this rectangular is converted into polar so that we can get magnitude and angle. So this is the total current flowing through this resistor 2 ohm due to 5 voltage source as well as 10 voltage source. So in this problem we discussed the superposition theorem, the AC source having the AC source having with 2 sources. We consider the first source, calculated the current, then we consider only second source, we calculated the current, then both are added together. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the solved problem based on the superposition theorem contained AC circuit. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. The problem statement is use the superposition theorem to find the current I0 in the circuit shown below. We need to find the current I0 for the given network. So this is a given network. So this is I0. We need to find the current I0 here. Having the one current source is available and one voltage source is available. Then this capacitor, inductor, 2 resistors are available. So based on the superposition theorem, the current I0 equal to I0 dash plus I0 double dash. I0 dash is current due to voltage source alone. I0 double dash is current due to current source alone. So in superposition theorem, first we need to consider only current source. We need to remove the voltage source by short circuit. Then we need to find the current I0 due to the current source alone. The second step, we need to consider only this voltage source. We need to remove this current source by open circuit. We need to find the I0 again. So the total current is I0 dash plus I0 double dash. So that is the principle of the superposition theorem. So based on that, first we will go find the I0 dash. That is, we are going to consider only current source. We are going to remove the voltage source. Now we will go to the step 1. So step 1 is consider only 20. First we are considering voltage source. Then we will go to current source. Step 1 is for current voltage source. Step 2 is the current source. Voltage source and remove the current source. Remove the current source means open circuit. So here the current source is removed and kept open. Right? Only now voltage source is available. Now we need to find current flowing through this circuit, I0. Right? So by seeing this diagram, we need to simplify this circuit in order to find the current I0. So due to this open circuit, by inspecting this circuit, we can easily understand that these two are connected in parallel. This 8 ohm and J10 ohm inductor, these two are connected in series, not parallel, connected in series. That is parallel with this capacitor. Right? So these inductor and resistor are connected in series. There is no branch here, connected in series. That is parallel with this capacitor. So based on that, we can find the Z equivalent. 8 plus 10J, that is this combination, resistor and inductor, is parallel with the minus 2J, that is a capacitor, right? So Z equivalent equal to minus J2 into 8 plus J10 divided by minus J2 plus 8 plus J10, that is R1 into R2 divided by R1 plus R2, that is the basic formula, right? So after simplification, step by step we need to simplify this. So it is multiplied inside minus J16 minus J square 20 divided by 8 plus J8, right? So here the 8 is taken outside. This 8 is taken outside, minus J2 minus J2.5. Here also 8 is taken outside, got cancelled, right? So J2 minus J square is minus 1. Minus 1 into 2.5 divided by 1 plus J. So minus J2 plus 2.5. Here already one minus is there, already one negative is there. So plus 2.5 divided by 1 plus J. So for further simplification, it is multiplied and divided by 1 minus J into 1 minus J. That is complex conjugate of 1 plus J in order to bring in the simplified form. The complex conjugate of 1 plus J is 1 minus J divided by 1 minus J. Is multiplied and divided by 1 minus J. Right? So it is multiplied here. We will see the further simplification. Before that, we will see this circuit diagram. Right? So after simplification, what we got? 0.25 plus minus J 2.25. That is the Z equivalent. Right? We will see this Z equivalent later. Before that, we will see this diagram. Right? So this 4 ohm and minus J2 ohm is already available. We will refer the diagram. This 4 ohm and J2 ohm already available. This entire circuit is now simplified into 0.25 ohm minus J 2.25 ohm. Right, now see the circuit diagram is now simplified. All are saving single circuit, single loop is there. So current flowing through all the elements are equal because of single loop. Right, so that the total impedance ZT is nothing but sum of all these 4 minus J2, that's already available. After simplification we got 0.25 minus J 2.25, right? So 4 minus J plus 0.25 minus J 2.25. So the total impedance is 4.25 minus J 4.25. So both are the same, real term and imaginary term. Here positive, here negative, right? So this is the final impedance of the circuit. Now we will continue this. How we are getting this? 0.25 minus J 2.5. For this Z equivalent, that is the two parallel combination. Here the further simplification we will see that. So that we will verify this answer. So this is the final impedance. So for further simplification of Z equivalent, minus J2 plus 2.5 plus J square 2 minus J 2.5 divided by 1 square minus J square. In order to cancel this complex number, we multiplied with complex conjugate, multiplied and divided by complex conjugate, right? So that is simplified, further simplified. 1 minus J square is minus 1. See, now it is from 1 plus 1. The complex number is now removed. So that is our aim, so that we multiplied and divided by the complex conjugate. So after simplification we got 0.25 minus J 2.25. So this is the circuit, that circuit is available. Now we verified that. Now the Z equivalent is verified, and we also got the total impedance. From the circuit diagram we already discussed the total impedance. Now we can find the current. Because of single loop, the current flowing through all the elements are equal. So we can say I naught dash, right? This is our requirement. This I naught dash means current due to only voltage source. So J20, that is the voltage source, divided by total impedance 4.25 minus J 4.25. This already we discussed, right? So 20J divided by 4.2 is taken outside, 1 minus J. So here also, in order to remove this complex, it is multiplied and divided by complex conjugate. 1 minus J complex conjugate is 1 plus J. So multiplied and divided, so the original term will not affected. So 20 divided by 4.25 is 4.7. So 4.7 this j and these are multiplied. J into 1, j. J into j, j square. Similarly here, 1 minus j, 1 plus j. A minus b, a plus b is a square minus b square. A is 1, 1 square. B is j, j square. Right? Now we can go for further simplification. So 4.7 into this j is taken, j plus this j square is minus 1. Similarly 1 minus this j square is minus 1. So 4.7 minus 1 plus j, this minus 1 plus j, this 1 minus of minus 1, so it become 2. So minus 1 plus j divided by 2. So 4.7 divided by 2 is 2.353 minus 1 plus j. So it is multiplied inside. So I naught dash is minus 2.353 plus j 2.353. So this is the current due to the voltage source alone. So that I naught dash. Now we need to consider the current source. By removing the voltage source, we need to find I naught double dash. So the step 2, consider the 5 ampere current source and voltage source is removed by short circuit. Now here we will consider only current source. So they see the diagram, the equivalent diagram, the current source is considered. The voltage source what available here is removed and short circuit. Right? Now the equivalent circuit is available. After removing the voltage source, this equivalent circuit is available. Now we can go for the Kirchhoff's voltage law, loop method. Right? Nodal loop analysis. By using KVL, we can apply the KVL and we can find the loop current. So this is the first loop. This is the first loop, means closed circuit. So current flowing through the first loop is I1. This is the second loop. Current flowing through the second loop is I2. This is the third loop. Current flowing is I3. So our aim is to find I2 because I naught double dash. Current due to current source is I naught double dash. That is nothing but I2. So only we need to find I2. I1, I2 is, I1, I3 is not needed. What we need is current flowing through this circuit network. So I2 is needed. Now we can apply the KVL to the loop 1, first loop. Right? So this is the first loop. So here 8 ohm available, inductor available and capacitor available. In this resistor only I1 is flowing. In this inductor I1 as well as I3 because inductor is connected between first loop and third loop. This capacitor is connected between first loop and second loop. So I1 and I2 is flowing in capacitor. I1 and I3 is flowing in inductor. Only I1 is flowing in resistor. So based on that 8 into I1 plus J10 I1 minus I3 inductor connected between 1 and 3 is minus because see the direction both are different. This is flowing in this side towards left. This is going towards right. So both are opposite direction. So I1 minus I3. Similarly minus J2 I1 minus I2. This capacitor connected between the first loop and second loop. So I1 minus I2. So we got this equation that is equal to 0. There is no voltage source available in the loop 1. So after simplification step by step we got 8 plus 8j into I1 plus J2 I2 minus J10 I3. So after simplification we can take it as equation number 1. Now apply the Kirchhoff's voltage law to the second loop. In this second loop what we have? This capacitor, one more capacitor and this resistor. This resistor only I2 is flowing because it is individually available. But this capacitor connected between third loop and second loop. So I2 also flowing, I3 also flowing. This capacitor connected between 1 and 2. So I1 also flowing, I2 also flowing. So based on that 4 into I2 minus plus J2, I2 minus I1. So this capacitor I2 minus I1. Here loop 2 means I2 as a reference. Loop 1 means I1 as a reference. From I1 I3 is subtracted. From I1 I2 is subtracted. Loop 2 means from I2 I1 is subtracted. For this capacitor I2 minus I3. Second loop minus third loop. So after simplification what we got? 4. This further simplification is there. So J2 I1 plus 4 minus J4 I2 plus J2 I3. It's the second equation. Right. In the loop 3, the third loop. Third loop, this 5 ampere was current is available. So I3 equal to 5. Directly we can write I3 equal to 5. No need to write the equation. If you write the equation, that also no problem. But we have the answer is there. Here one current source is there. So current flowing through this loop is 5 ampere. So that is written directly. So our aim is to find the I2 value, because I naught double dash is I2. Here the current flowing at this network. So that we can do by simplifying the equation, we can find the I2 value. So equation 1 is written as it is. It is further simplified. This equation 2 is written as it is. Right? Then it is divided by 2. So that it is simplified. Everywhere 2 is available. Right. From that I1 is written. I1 equal to, in terms of I2. Right. Minus 2 minus of 2 minus J2 into I2 minus 5 Ij divided by I. Right. So equation 1 is available. Equation 2 is simplified. Divided by 2. I1 is written in terms of I2. Right. So further it is multiplied and divided by the J in order to go for further simplification. Multiplied and divided by J, so that we can remove this J. The J by J. So it is multiplied. J square value is minus 1. Right. So that the denominator is now removed. So this minus is multiplied inside. So that minus of mod multiplied, it is available here. So this term is multiplied. Minus of minus 2J plus 2J square into I2 minus 5 of minus 1. Now we can go for further simplification. So it is multiplied inside and further simplified. Finally we got I1 equal to 2 plus J2 into I2 minus 5. So I1 is available in terms of I2. Now we can substitute this. Substitute I1 in equation 1. Right. So now we got this value. I1 value is got. This I1 value is we are going to substitute in the equation number 1. What is equation number 1? This is equation number 1. 8 plus J8 I1 plus J2 I2 minus J10 5 equal to 10. So in this I1 is substituted here. This value is substituted. So for that we can go for further simplification. We need to multiply inside step by step and we have to simplify. Right. The step by step it is multiplied. So finally what we got, I2 into 34J minus 90J minus 40 equal to 0. Right. We got the simplified. After simplification we got this value. So that I2 equal to, other terms are brought in the right hand side. 90J plus 40 divided by 34J. In order to for further simplification, it is multiplied and divided by J. Then it is multiplied here. So that 90 plus J plus 40 into J divided by 34 J square. J square value is minus 1. So it become minus 34. That is the advantage to multiply and divide by J. So that is further it is multiplied inside. Again J square minus 1. Right. So minus 90 plus 40J divided by 34. Right. That is for now it is divided. 90 divided by 34 is 2.647. 40 divided by 34 is minus 1.176. See this, now we got the I2 value. So that is our requirement. That is current due to only the current source is I2. Now we will go for further simplification. So I double dash equal to minus I2. So the direction is both is different. By inspecting the diagram we can easily understand. I naught double dash is going upward direction, but I2 is going downward direction. So that due to the negative. So negative of 2.647 minus J 1.176. Multiply negative inside. So minus 2.647 plus, already here negative is there, plus J 1.176. Now we got the second step, current due to current source alone. Now we need to find the total current. Right? The total current is nothing but current due to current source as well as voltage source. I naught equal to I naught dash plus I naught double dash. I naught dash due to voltage source, we already calculated in step 1. I naught double dash is due to current source alone. In step 2 we calculated. Both are added together, minus 5 plus j 3.529 in a rectangular form. While converting polar form, you can convert directly using the calculator. 6.12 with an angle of 144.78 ampere. So this is the I naught value. So in this problem, we solved the superposition theorem. We've calculated the I naught value having one voltage source and one current source. In step 1, we consider only voltage source, current source is removed. In step 2, current source is considered and voltage source is removed, and we calculated the current. So finally we added both the currents so that we got the final value. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the details about maximum power transfer theorem. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, maximum power transfer theorem. We'll see the case 1. Purely resistive circuit and the load resistance is variable. The circuit is contain only resistance and the load also resistance, that is variable. The statement of the maximum power transfer theorem is maximum power will be delivered from a voltage source to a load when the load resistance is equal to the internal resistance of the source. This is the statement given. Maximum power will be delivered from the voltage source to the load when the load resistance is equal to the internal resistance, right? If the load resistance is equal to the circuit resistance, the maximum power will be delivered from voltage source to the load. That is the statement given. Now consider this circuit. We will verify this statement. Consider a voltage source of generated voltage Vg and internal resistance Rg connected to a load RL as shown in the diagram. Right? So we have the voltage source Vg. This is the load resistance, load current, the terminal AB. The load resistance is marked as terminal AB. The Rg is the internal resistance. So based on the maximum power transfer theorem, this Rg is equal to RL. Both are equal. If it is both are equal, then this voltage source will deliver maximum power to the load. That is the statement given, right? So we have voltage source, internal resistance, load current. This load resistance is marked as terminal AB. Now we'll go for the further derivation to verify how the maximum power is delivered to the load. When the power transfer to the load is maximum, RL equal to Rg. That is the condition given. So RL equal to Rg when the maximum power is delivered to the load. At this condition, the total resistance is Rg plus RL. So we'll take it as 2RL. Both are equal. So we'll take it as RL equal to Rg equal to RL. So the RL plus RL, 2RL. So based on that, the load current IL equal to V by R. Voltage is Vg, voltage source. The resistance is 2RL. So IL equal to Vg divided by 2RL. Right? So from the condition, we start from the condition maximum power transfer theorem. When the power is transferred to the load is maximum, the load resistance equal to system resistance, internal resistance. So at this condition, the total resistance is Rg plus RL. So it becomes 2RL. From that we can calculate the load current IL equal to Vg by 2RL. Vg is the voltage source available in the circuit divided by total resistance 2RL. From that we can find the power delivered to the RL. The formula is I square RL. There are three formula available. V into I square R, V square by R. In that we are using this I square R, IL square into RL. So IL square already calculated, Vg by 2RL. So Vg by 2RL square into RL. So while squaring, it is Vg square divided by 4RL square into RL. Right? One RL got cancelled. Here RL available, here RL square is available. So one term got cancel. So finally we have Vg square divided by 4RL. Power delivered to the RL is Vg square divided by 4RL. So after implementing the condition, after simplification, we got this equation, power delivered to the load. So in the maximum power transfer theorem, the condition is given means we can use this formula for maximum power delivered to the load. Vg square divided by 4RL. I will go for the further details. So based on that, the maximum power delivered to the load. So power delivered to the load, the condition is given, maximum power will be delivered to the load, so that it become a P max. So we calculated power delivered to the load based on the maximum power transfer theorem. That power delivered is a maximum power because it is condition is given. When RL equal to RG, the maximum power will be delivered. So P max equal to Vg square divided by 4RL. So this is the formula to find the maximum power delivered to the load. When the condition is given in the problem itself, we can use this formula. So the second case, the reactance is present. Previously we have only resistance and load resistance, and the reactance can be independently varied. The load is contained resistance, but the system contain, the circuit contain the reactance. So what is the statement given? Maximum power will be delivered from a voltage source to the load when the load impedance is a complex conjugate of the source impedance. In previous case, the internal resistance is equal to load resistance. But here the reactance available, so we have the complex conjugate. The complex number will be there, the real term and imaginary term, because of reactance. It may be the capacitive reactance or inductive reactance. So that the same condition is here also same. Power delivered will be, maximum power will be delivered from the voltage source to the load. Only the condition is load impedance is complex conjugate of the source impedance. Both are complex conjugate. Complex conjugate means A plus JB means the complex conjugate will be A minus JB, right? The load impedance and source impedance are complex conjugated. Now we'll see the further derivation, further details about the case 2. So ZZ, the internal impedance of the source, we can take RG plus JXZ, right? Previously we have only resistance, now we have impedance also, right? So RG plus JXG. Then ZL is RL plus JXL, load reactance but not inductive reactance, right? So this is the system internal impedance, this is the load reactance. So based on the condition, both are complex conjugate. According to the maximum power transfer theorem, ZL equal to complex conjugate of ZG, that is RG minus JXG, right? So ZL equal to ZG, but it is complex conjugated. Previous case what we have, RG equal to RL, right? Load resistance equal to system, the internal resistance. Here load impedance equal to internal impedance, but it is complex conjugated, RG minus JXC, right? Okay. Then we'll go to the third case. Reactance present, but only the magnitude of the load impedance can be varied, right? Only the magnitude is varied. Here also reactance is present. Now we'll see the statement. What is the statement of this? Maximum power is delivered from a voltage source of a load when magnitude of load impedance is equal to magnitude of source impedance. Previously we have complex conjugate. Now here only concentrating the magnitude. So magnitude of load impedance equal to magnitude of source impedance, right? Only we have concentrated the magnitude. So let theta be the angle of the load impedance, the angle of the load impedance, so that ZL equal to ZL angle theta, that is ZL cos theta plus JZL sin theta. This is the polar form, this is the rectangular form. Polar form we have magnitude and angle. Rectangular form we have real number plus imaginary number, real term plus imaginary term, right? So P equal to Vg square ZL cos theta divided by Rg plus ZL cos theta square plus Xg plus ZL sin theta square. So this is based on the previously we have Vg square divided by 4RL. Based on that we obtain this formula, right? P equal to this Vg by R. We concentrated only the magnitude, right? So this is the resistive term, reactive term. So the maximum power, for maximum power transfer, dP divided by dZL equal to 0, right? In order to get the maximum condition for maximum power, this equation is differentiated with respect to ZL, because ZL is a variable, right? Load impedance. So that is equal to 0. By equating 0, we are able to get the condition for maximum power transfer. Now we'll see the condition. So using this condition and simplifying the above equation, the simplification is not given, directly the expression is given. Rg square plus xg square equal to magnitude of ZL square. That is magnitude of ZZ equal to magnitude of ZL, right? So the derivation is not given, directly we have the expression is given. So the third case is nothing but magnitude. Magnitude of the internal impedance equal to magnitude of the load impedance. Both are equal, right? So we have further some more details are available. It may be mentioned that this condition hold good for a transformer where the turns ratio is varied for a maximum power transfer theorem. So it can applicable for the transformer also, right? So we will go for some more details. If the source impedance is purely resistive and load impedance consists of variable RL and fixed reactance X, then the maximum power transfer theorem. Maximum power transfer is RL square equal to Rg square plus X square, right? The source having the only impedance and load impedance consists of RL as well as reactance. If all these things are available, then it is RL square equal to Rg square plus X square, right? RL square is the load resistance. Rg is the internal resistance. X is the variable reactance that consists of the variable reactance X. If the load impedance is purely resistive equal to RL, but the source impedance consists of both resistive and reactance, then the power delivered to the load can be maximum by varying RL. The power transfer theorem is maximum when the power transfer is maximum when RL square equal to Rg square plus X square. Otherwise, RL equal to ZZ, right? So only RL is contained. Resistance contain only RL, but source contain resistance and reactance. In that case, what is given, that we can vary the RL value so that we'll make the both are equal and we can get the maximum power transfer. So that is RL square equal to Rg square plus Xg square. So these two is constant, but we can vary this. By varying this, we will make both are equal. Under that condition, RL equal to magnitude of ZZ, right? We'll go for further conditions. When conditions for maximum power transfer to the load are satisfied, the load is said to be matched to the source. That is, load and system source are equal. For solving any problem on maximum power transfer theorem, get the Thevenin equivalent for the given circuit, right? So while doing all maximum power transfer theorem, the first step is we need to get the Thevenin equivalent circuit. What is Thevenin equivalent circuit? Voltage source connected in series with the impedance, Thevenin impedance, right? VTH connected in series with RTH. RTH is nothing but system impedance, the internal impedance. So that the maximum power transfer theorem is very simple. This internal impedance is equal to load impedance. So if we got the Thevenin equivalent, it is a simplified circuit contain only voltage source and one internal resistance. So we need that internal resistance. Internal resistance equal to load resistance. So that the fully circuit will be, the complicated circuit will be simplified after getting the equivalent, Thevenin equivalent circuit. From that we can easily identify the system internal resistance that is equal to load resistance. So in this video we discuss about the maximum power transfer theorem. The condition for maximum power transfer theorem. Finally we got the maximum power delivered to the load, Vg square divided by 4RL. That formula can be used when the power delivered is maximum. We also discussed the reactive cases, case 2 and case 3, variable or magnitude. In that, finally the important thing is we need to find the Thevenin equivalent. Before going to proceeding, we need to find Thevenin equivalent. From that, we can easily calculate the maximum power transfer to the load. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the solved problem based on the maximum power transfer theorem for a DC circuit. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. The maximum power transfer theorem solved problem have DC circuit. The circuit shown below R observe maximum power. Compute the value of R and maximum power. So the circuit is contained 20 ampere current source is available. This is the load resistance. It marked as AB and 3 resistance are available, 5 ohm, 2 ohm and 3 ohm. The condition given is this R is observing maximum power. So we need to find the value of this R and what is the maximum power observed. So the condition is given. The load resistance is observing maximum power. So we can implement the maximum power transfer theorem. What is maximum power transfer theorem? When the load is observed maximum power, the load resistance equal to internal resistance of the circuit. Internal resistance of the circuit is equal to load resistance when the load is observing maximum power. So for that, we need to find what is the internal resistance. That should be equal to R value, load resistance. For that, we are having the Thevenin equivalent circuit. The Thevenin equivalent circuit is nothing but one voltage source contained in series with the internal resistance. So that it will be very easy for us to go for further process. So the Thevenin equivalent circuit is Thevenin voltage in series with the Thevenin resistance. This Thevenin resistance is nothing but the internal resistance of the circuit. This Thevenin voltage is nothing but when the load terminals are open circuited and find the open circuit voltage, that is V Thevenin. This R Thevenin is nothing but by removing all the voltage and current sources, we need to find what is the internal resistance of the circuit. So in that we can draw this the load resistance R with the terminal AB. So the complicated circuit can be simplified with the Thevenin equivalent circuit. After getting Thevenin equivalent circuit, it is easier. This RTH equal to R. That is the condition of the maximum power transfer theorem. So already given maximum power is transferred, so that this load resistance equal to Thevenin resistance. So by finding this Thevenin equivalent, we can easily equate these two values, right? So first we will find the Thevenin resistance, V Thevenin. So the 20 ampere source is available. This 5 ohm, 2 ohm and 3 ohm. The load terminal is open circuit. So V Thevenin is nothing but open circuit voltage, right? So we need to find what is the voltage across VAB. That is nothing but V Thevenin. Here the current source is available, 20 ampere. So the current 20 ampere will flow here. At this point, the current will be diverted. The current will divert here. Here 5 ohm is available. So these two are connected in series. So 2 plus 3, this is also 5 ohm. The current will not go to the open circuit. The current will go to this 5 ohm resistor and remaining will go to this 2 ohm and 3 ohm. That is total of 5 ohm resistor. Both are equal. This is 5 ohm. This is also 5 ohm. So current will be equally divided, 10 ampere and 10 ampere. Total 20 ampere, 10 ampere flow through this 5 ohm resistor. Remaining 10 ampere will flow through this 2 plus 3, 5 ohm resistor. Right? So the equal amount of current will flow in the both the branch. Now we got the value of current flowing through this 3 ohm resistor. So V Thevenin, that is VAB, is nothing but voltage drop across this 3 ohm. Right? So V Thevenin equal to VAB, that is nothing but voltage drop across 3 ohm. Both are parallel. So that by finding the voltage drop across 3 ohm, we can easily find the VAB or VTH. right? So V equal to I into R. I is 10 ampere. R is 3. So minus, it is going down. So minus. So minus 30 voltage. So the voltage across 3 ohm is 30 voltage, that is VAB, that is VTH. Now we calculated the Thevenin voltage. Now we will find the Thevenin resistance, RTH. Right. What is RTH? The resistance across AB. We need to remove the voltage and current source. If you remove voltage source, that is short circuited. If you remove current source, it is open circuited. We have to keep the circuit in open condition. If it is current source, open circuit, voltage source means short circuit. So here we have current source, so it is open circuited. We need to find what is the resistance across AB. So current will flow through this. At this point, the current is diverted. So we need to follow from this side onwards, not from this side, not from source side, from load side. That is the RAB is the R Thevenin. So we have to follow from this load end. So current is diverted here. So this 3 ohm and here 2 and 5 ohm is there. Current will not go to open circuit. So that 2 plus 5 ohm are connected in series. That is connected in parallel with the 3 ohm. Right? So current is divided in this 2 branch. So these 2 branches are parallel, 3 ohm. Here another 5 ohm is there. So both are same amount of current is flowing through 2 ohm and 5 ohm. Current will not go to open circuit. So 2 plus 5, 7 ohm is one resistor and 3 ohm another resistor. Both are connected in parallel. So the R Thevenin equal to this parallel combination is nothing but R Thevenin. R1 into R2 divided by R1 plus R2. So 3 into 7 divided by 3 plus 7. 21 divided by 10, that is 2.1 ohm. Right? So the Thevenin resistance is 2.1 ohm. This Thevenin resistance is nothing but internal resistance of the circuit. Right. Now we'll go to the next one. So we calculated the Thevenin resistance and Thevenin voltage, that based on the according to the statement of maximum power transfer theorem, the value of R for maximum power transfer to is RTH. We already discussed that the load resistance equal to internal resistance. Internal resistance we calculated 2.1 ohm. RTH is 2.1 ohm. Right? So the same value is applicable for load resistance. Load resistance also 2.1 ohm. So that only we are calculating Thevenin equivalent circuit. Thevenin equivalent circuit contain VTH and RTH. That RTH is nothing but internal resistance. Based on maximum power transfer theorem, internal resistance equal to load resistance. Right? So internal resistance is 2.1 and load resistance also 2.1. So under that condition, the maximum power transfer, we have formula is available. Right? The details about maximum power transfer theorem explanation available in separate video. So this is the formula, V square TH divided by 4RL. Right? RL value is 2.1 ohm. So that is also one of the question. RL value is 2.1 ohm. The maximum power transfer, we have formula is available. Right? Thevenin voltage we already calculated. So VTH divided by 4 into RTH. Both are equal. RL equal to RTH. So V Thevenin is minus 30 square divided by 4 into R Thevenin is 2.1 ohm. So by simplifying we got 107 watts. So this is the maximum power delivered to the load. So in this we need to calculate two parameters. One is maximum power delivered to the load and the load resistance. Load resistance is nothing but 2.1 ohm because load resistance and Thevenin resistance both are equal. So that we are calculated V Thevenin and R Thevenin. So in this problem we use the maximum power transfer theorem. We calculated the value of load resistance and maximum power delivered to the load resistance. For that we use the Thevenin equivalent circuit, V Thevenin and R Thevenin. R Thevenin is nothing but is equal to load resistance based on the statement of the maximum power transfer theorem. This V Thevenin we can use for finding the maximum power delivered to the load, V Thevenin and R Thevenin. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the solved problem based on the maximum power transfer theorem contained the DC circuit. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Find the value of RL for maximum power delivered to it and also maximum power delivered value. Right? So in the circuit is given. In this, we need to find the RL value, load resistance. The condition given is maximum power is delivered to the load, and also the value of what is the maximum power delivered to the load. We need to find two values, this RL value as well as maximum power delivered to the RL. So the condition clearly given, maximum power is delivered, so we can implement the maximum power transfer theorem to this circuit. So the load terminal is marked as AB. So we have two voltage sources available, 12.5 voltage with internal resistance 0.4 ohm and 1.7 voltage with internal resistance 0.6 ohm, and four resistors are available, 1.2 ohm, 1 ohm, 1.4 ohm and 1.4 ohm. So in order to implement the maximum power transfer theorem, we need to find the Thevenin equivalent circuit. What is Thevenin equivalent circuit? Thevenin equivalent circuit consists of the VTH and RTH, voltage source in series with the resistance. What is VTH? It is the open circuit voltage. The load terminal is open circuited and voltage across the AB is nothing but VTH. What is RTH? Is the resistance across the AB by removing the voltage and current source. So by removing voltage and current source, the resistor available across AB is nothing but RTH. So this RTH is nothing but system resistance, internal resistance, right? So this we have internal resistance. So based on the maximum power transfer theorem, this internal resistance is equal to load resistance. So by after calculating Thevenin equivalent circuit, it will become easier. We have voltage source, only one voltage source. The complicated circuit is reduced into only one voltage source and only one resistance. That is nothing but a internal resistance. Based on the statement, these two are equal. So we can get the simplified circuit. We can easily calculate the R value. R value is nothing but RTH. And maximum power delivered to the load formula is available. VTH divided by 4 into RTH. V square by R. The formula is available. So by finding Thevenin equivalent circuit, we can easily calculate the value of R as well as power delivered to the R, because this is the system internal resistance. Condition is internal resistance equal to load resistance. Right. Now we'll go for Thevenin equivalent circuit. First we will find the V Thevenin. First we will find V Thevenin. To find V Thevenin, disconnect the R. The load resistor is open circuited. Right. So now we need to find the voltage across AB, that is nothing but VTH. VTH is nothing but voltage across AB by making open circuit. Right. How to find this VTH? That is, first we will find the current. This VTH is nothing but VAB, voltage across AB. Either this side you can calculate, because voltage across AB equal to voltage drop across this side or that side. Either this side or that side. For that we need first find the current, because this is already one voltage source is available. Then here two resistors are available. Some of the voltage will be dropped across. So from the voltage source, from this voltage value, if we subtract the voltage drop across these two resistors, we will get AB, VAB. Similarly, from this voltage source, if we subtract the voltage drop across these two resistors, we will get VAB or VTH. Either side we can use. In both the cases we need current value. So what is the current I? I equal to V by R. What is the V? Voltage? Two voltage sources available, 12.5 and 1.7. So the difference between these two is the total voltage, 12.5 minus 1.7, divided by the total resistance. What are the resistance available? This is the internal resistance of the voltage source, 0.4, 1.2, 1. Internal resistance of second voltage source, 0.6, 1.4 and 1.4. Right? 1, 2, 3, 4, 5, 6 resistors are available. All are added. 1, 2, 3, 4, 5, 6. So after simplification we got 1.8 ampere, right? The current flowing through the circuit is 1.5 ampere. Now we'll find the Thevenin, V Thevenin equal to VAB. So we calculated from that side. We are not, this side also we can calculate. So 1.7 voltage is available. 1.7 voltage is available. See the current value, current is flowing downwards, that is positive terminal to negative terminal. So drop in voltage minus 1.7. Minus, we have to subtract the drop across these two voltage sources. Voltage drop is V equal to I into R. I is 1.8 ampere. The R value is this 1 ohm and 1.4 ohm as well as this 0.6 ohm internal resistance of the voltage source. There also some voltage will be dropped. So 1 plus 0.6 plus 0.4, right? So this is the total voltage source available. From there we are subtracting the voltage drop across the resistor. Voltage drop across the resistor is V equal to I into R. I value is 1.8. R value is these three. 1 plus 0.6 plus 1.4. Now we'll find the value. So the simplified value equal to VTH equal to VAB equal to minus 1.7 minus 1.8 current. This is the total resistance into 3. After simplification we got minus 7.1. Both are negative, minus 7.1 voltage. So V Thevenin equal to minus 7.1 voltage. Now we'll find the R Thevenin value. R Thevenin is nothing but the resistor across AB by removing the voltage source, voltage and current source. Here we have two voltage sources available, that is removed. If you remove the voltage source, it's short circuit. By removing current source is open circuit. So here one voltage source, here one voltage source, both are removed, but that contain the internal resistance, that is calculated, that is added 0.4 ohm and 0.6 ohm, right? Both are taken into account. Sometimes the problem not given internal resistance, but in this problem internal resistance are given, so that is calculated. So we need to find what is the resistor across AB. So this side one circuit is available, this side one circuit is available. So current at this point is divided. It means these two are parallel. The same current is flowing through all three resistors. Same current is flowing through all three resistors. That means these three resistors are connected in series. These three resistors are connected in series. Then both are parallel. So that is given here. 1.2 plus 0.4, 1.6 plus 1.4, 3 ohm. 1 ohm plus 0.6, 1.6 plus 1.4 is another 3 ohm, right? So this branch is connected in series 3 ohm. This branch is connected in series 3 ohm. Both are in parallel, right? So RTH RAB equal to R1 into R2 divided by R1 plus R2. 3 into 3 divided by 3 plus 3. That is 9 by 6. It is 1.5 ohm. If both resistors are equal, we will get half of the value, 1.5. Directly also you can write. 3 ohm and 3 ohm connected in parallel mean half of the value, 1.5 ohm. Now we got the V Thevenin value as well as R Thevenin value. We can draw the Thevenin equivalent circuit. So this is the Thevenin equivalent circuit. VTH is minus 1.7 minus 7.1 voltage. RTH is 1.5 ohm. This is the load terminal RL. So based on the condition what is given, this RTH equal to RL. So RL value is nothing but 1.5 ohm. Right? That is the advantage of this Thevenin equivalent circuit. The complicated circuit is simplified with a single voltage source and resistance. This resistance is equal to RL based on the maximum power transfer theorem. Then how to find the maximum power transfer? According to the statement of maximum power transfer theorem, the value of RL for maximum power to transfer is RTH equal to RL. Both are equal. That is 2.1 ohm. And the maximum power transfer formula is available. VTH square divided by 4RL. This is the formula to find the maximum power transfer under the condition. This RL is nothing but RTH. Both are equal. So VTH square divided by 4RTH. That is equal to 7.1 square divided by 4 into 1.5. That is 8.4 watts. So maximum power delivered to the load is 8.4 watts. So we calculated load resistance value, also maximum power delivered to the load. So in this problem we discussed the maximum power delivered to the load and maximum on the RL value by using maximum power transfer theorem. For that we calculated the Thevenin equivalent circuit, VTH and RTH. This RTH is equal to RL, that is the advantage, and also maximum power is calculated from this formula. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the solved problem based on the maximum power transfer theorem contained AC circuit. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. A loudspeaker is connected across the terminal AB of the network shown below. What should be the value of impedance of the speaker to obtain maximum power transfer to it, and what is the maximum power? So the network is given across this AB, the loudspeaker is connected, so that we need to find the value of impedance of this loudspeaker and also maximum power transfer to this loudspeaker. So it is clearly given maximum power is transferred to the load. So the loudspeaker is taken as load that is connected across AB. So the maximum power is transferred. So we can use the maximum power transfer theorem for this network. What is the maximum power transfer theorem? The impedance of the circuit is equal to impedance of the speaker. Impedance of speaker and the internal impedance both are equal. That is the condition given by maximum power transfer theorem. So based on that we can proceed. The first step is we need to find the Thevenin equivalent circuit. Thevenin equivalent circuit we need to find, that is V Thevenin in series with the Z Thevenin. Voltage source in series with the impedance. This voltage source is nothing but the voltage across AB, Thevenin voltage. By making the load terminal open circuited, the voltage across AB is nothing but V Thevenin. The Z Thevenin is nothing but the Z impedance across AB by removing the voltage or current source. Current and voltage source is removed and impedance across AB is nothing but Z Thevenin. So by finding this V Thevenin and Z Thevenin, the advantage is this Z Thevenin is equal to load impedance, because the condition in the maximum power transfer theorem is the load impedance equal to internal impedance. So this is nothing but internal impedance. This complicated circuit is simplified with one voltage source and system or internal resistance or impedance. This is both are equal. So we can easily calculate the load impedance value, that is nothing but Z Thevenin. So that is the advantage of this circuit. And also we can calculate the maximum power. The formula is available. V Thevenin square divided by 4RL. That is the formula we can easily implement. We can use the formula after finding this Thevenin equivalent circuit. So first we will find the V Thevenin. How will you find the V Thevenin? V Thevenin is nothing but voltage across AB. So that is nothing but voltage across this capacitor, because both are connected in parallel. So voltage across capacitor V equal to I into R, I into Z. Z value is minus J5. We need I value. What is the current flowing through this capacitor? So that we can find I into minus J5 will give the voltage across AB. How will you find the I value? I equal to V by R. V is nothing but 10 voltage with an angle 30. Divided by R means impedance. We need to add all this. All are connected in series. This resistor, inductor, capacitor are connected in series. So this V divided by impedance will give the R value. R into this impedance will give the V Thevenin or VAB value. Right? Now we'll find the V Thevenin value. So in the original circuit, the current I equal to voltage source 10 of angle 30 degree divided by adding this all resistor, inductor and capacitor, 3 ohm, J4 minus J5. So 10 with an angle 30. So this is my plus J4 and minus J5. So that J1, 3 minus J1. So 10 with an angle 30 degree. This is the rectangular form. We have divider is there. For division and multiplication, polar form is enough. Polar form we need to find. For addition and subtraction, this rectangular form is enough. So this rectangular form is now converted into polar form. How to convert? This is magnitude, this is angle. Magnitude is nothing but square root of 3 square plus 1 square. That is real term square plus imaginary term square. Tan inverse b by a, imaginary term divided by real term, minus 1 by 3. Right? So after simplification, what we got? 10 with an angle 30. So this value is 3.16. The angle is minus 18.4. Right? So this division is there. So the 10 divided by 3.16. So that it will give 3.16 ampere. Then angle is subtracted. 30 minus 18.4. Right? So this minus become plus. So 48.4 angle. So the value is 3.16 with an angle of 48.4 degree ampere. So the current value is calculated 3.16 magnitude with an angle 48.4 ampere. So the divided means these two values are divided, angle is subtracted. 30 minus of 18.4. So it becomes 30 plus 18.4 is 48.4. Now we calculated current value. So the Thevenin is nothing but voltage across the capacitor with the value minus J5. V equal to I into R. I value is 3.16 with an angle 48.4. The J value is J5. Right? So this is in the polar form. This also should be converted into polar form. That is 5 angle 90 degree. Minus J represent minus 90 degree. So every J represent my 90 degree, minus J represent minus 90 degree. Now this is multiplication. We need to multiply this. 3.16 into 5. 15.8. The magnitude is 15.8 voltage. The angles are added together. Here subtracted. 30 minus. Here added. So 48.4, but it is minus is there. 48.4 minus 90, it is minus 41.6 degree voltage. So the Thevenin value is magnitude is 15.8 and the angle is minus 48.16 voltage. Now we'll go to the Thevenin. So the next step, find the Thevenin, that is ZAB. The impedance across AB by removing the voltage source. By removing the voltage source, short circuited. If you remove current source, it will open circuited. Here voltage source, short circuited. We need to find the impedance from this side, not from the voltage source side, from the load side. So at this point, the current is diverted. So these two are in parallel. J5 is parallel with 3 plus J4. These two are in series. 3 plus J4 in parallel with minus J5. So that R1 into R2 divided by R1 plus R2. The two things are parallel. The formula is R1 into R2 divided by R1 plus R2. R1 is 3 plus J4. R2 is minus J5. So 3 plus J4 minus J5. Right. So 3 plus J4 minus J5. This J4 minus J5. So it becomes J1 minus J1. Right. So this should be converted into, this is the polar rectangular form. In order to divide it, we need polar form. So 3 square plus 4 square. This will give the magnitude. Tan inverse 4 by 3. Imaginary term divided by real term. B by A. Similarly 5 with an angle 90 degree. Just now we see that. We saw that minus J refers 90 degree. Minus 90 degree. Similarly here 3 square plus minus 1 square. Tan inverse minus 1 by 3. Right. So this is the procedure to convert rectangular form into polar form. The magnitude is calculated square root of square and angle is calculated tan inverse B by A. That is a formula for the converting rectangular to polar form. So for simplified, it is 5 angle 53, 5 angle minus 90, 3.16 angle 18.4. This already we calculated in previous case. This also we calculated. So now we have these two should be multiplied and divided by 3.16. So 5 into 5, 25 divided by 3.16, 7.91. These two angles are added and subtracted from this angle. So minus 18.4, right? 53 minus 90 minus 18.4. So we got minus 18.6 degree. So this should be converted into rectangular form for further process. How to convert this magnitude into cos of angle plus j into magnitude sine of angle. That is the procedure to convert polar form to rectangular form. 7.91 cos minus 18.6 plus j 7.91 sine 18.6. So this value is nothing but we need to find this cos minus 18.6 and sine 18.6, that should be multiplied. So this 7.1 and these two are multiplied. 7.5 minus j 2.52 ohm. Right? We got Z Thevenin equal to 7.5 minus j, this real term and imaginary term. This is Rg. This is Xg. So Z Thevenin equal to 7.5 minus j 2.5 ohm. Right? Now we calculated both Thevenin voltage as well as the Thevenin resistance VTH and RTH. So from that we can go for the further process. So this is the Thevenin equivalent circuit, V Thevenin, Z Thevenin and load impedance. What is the given condition for maximum power transfer to the loudspeaker? Let the load impedance ZL equal to RL plus JXL, both being variables, right? So RL is 7.5 ohm, 2.52 ohm. This 7.5 ohm, right? The Z Thevenin equal to ZL. Both are equal but complex conjugated. So 7.5 is written as it is, minus 2.52 is plus 2.52. Right? Both are complex conjugate. That is the condition given by the maximum power transfer theorem. Load resistance, load impedance equal to internal impedance. This is the internal impedance that is calculated from the Thevenin equivalent circuit. So both are equal, only it is complex conjugated. So ZL equal to 7.5 plus j 2.52 ohm. Right? So one question we answered, because we find the answer ZL, the impedance of the loudspeaker. Then what is the power? What is the power delivered to the loudspeaker? Before that we need to find current at the maximum power, VTH divided by 2RL. Right? So VTH, that VTH divided by, both are equal, so that 2 into RL. Right? Otherwise ZTH plus ZL. Right? So ZTH equal to ZL, so that 2R. This is one formula. So 15.8 angle 41.6 V Thevenin value divided by 2 into 7.5. This value, both are same. 7 plus 7.5 or 2 into 7.5. So the value is 1.053 with an angle 41.6. So the magnitude is 1.053 ampere. The current is flowing through the loudspeaker. From that we can find the power value, I square RL. So 1.053 into 7.5, it is 8.32 watts. So this is the power delivered to the loudspeaker. This is the maximum power. So we calculated the impedance of the loudspeaker, then current flowing through the loudspeaker under maximum power condition, and value of the maximum power 8.32 watts. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the solved problem based on the maximum power transfer theorem having AC circuit. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Determine the load impedance ZL in the network shown below for maximum power transfer. Find the energy delivered to the load in 1 hour. Right? We need to find the load impedance ZL value, that is indicated by AB. The condition given is maximum power is transferred. What is that maximum power transfer? We can use this maximum power transfer theorem, that is this ZL is equal to internal resistance. Internal resistance and ZL are equal. That is the condition given by maximum power transfer theorem. And also we need to find the energy delivered to the load in 1 hour. Right. So for that we need to find first the Thevenin equivalent circuit. What is Thevenin equivalent circuit? VTH connected in series with the ZTH. What is this VTH? This Thevenin voltage, that is open circuit voltage across AB. The load is removed and voltage across AB is calculated, that is V Thevenin. What is Z Thevenin? the impedance across AB by removing the voltage source. That is nothing but system impedance. That's a internal impedance, this is ZTH. Then this load terminal. What is the advantage of this Thevenin equivalent circuit? After this complicated circuit is simplified with voltage source and impedance, with only one voltage source and impedance. This impedance is the internal impedance. So condition of the maximum power is this internal impedance equal to impedance of the load. So we can got the value of load impedance, that is nothing but Z Thevenin. ZL equal to Z Thevenin. So we can easily calculate the load impedance from the Z Thevenin. And also we can calculate the power delivered, maximum power delivered using this voltage source. One formula is available, VTH square divided by 4 into RL. So that from this Thevenin equivalent circuit we can easily calculate the load impedance, that is equal to Z Thevenin, and also we can calculate the maximum power delivered to the load. Right? Now first we will find the V Thevenin. We will find V Thevenin. So here one voltage source is available 100 magnitude, one resistor available 100 ohm, and inductor J 200 ohm. This is the voltage across AB, that is V Thevenin. So this is nothing but both is parallel. So the voltage what is available here, that will be appear across AB. So V Thevenin equal to 100 voltage, right? So the voltage across AB is V Thevenin, that is nothing but voltage source. There is no drop, right? So the what is the voltage available, that will be appear across AB. So based on that, the power maximum, the formula is there in the maximum power transfer theorem. VTH divided by 4RL. So 100 square divided by 4 into 100, right? So this V Thevenin equal to 100 voltage we calculated. RL what we calculated is the 100 ohm, right? This both are equal. The load resistance equal to system resistance. So that is equal to 25 watts, right? From that we need to find the energy. What is the energy delivered in 1 hour? So energy is power into time, right? So this RL value is nothing but the system impedance, system resistance. They are not considered this inductance. So 100 ohm is nothing but the load inductance RL. RL is equal to 100 ohm. Both are equal based on the maximum power transfer theorem. So power we calculated 25 into time 1 hour. So 25 watt hour. If it is converted into the seconds, it is 25 into 3600. 6 seconds, 6 minutes, 36,000, 3600. So it is 90,000. So it is 90 kilojoules, right? This is given in watt hour, only 1 hour. This hour is converted into minutes, seconds, 3600 seconds. So that it got joules. This 90,000 by kilojoule, that is 90 into 10 to the power 3. So 90 kilojoules. So in this problem we calculated the Thevenin equivalent circuit. From that we calculated maximum power delivered as well as energy. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening.